Dear students, welcome to Lecture 11 on the topic of modelling. This lecture is an introduction to modelling. This lecture is part of the subject Future Farming Technologies, which is offered as a component of the Bachelor of Agriculture and Technology, a degree that you can obtain from either North Melbourne Institute of TAFE or Melbourne Polytechnic. Please visit our website at www.nmit.edu.au for further information on this course and other courses that we offer. My name is Dr. Nikki Cooley. In this topic we will be covering the following learning objectives. Learning 1, models enable us to understand the interrelationships between technology, performance, sustainability and production efficiency in agricultural industries. Learning outcome number 3 is specifically geared around the use of models, that is, to use crop model and yield production software to assess agricultural productivity. I hope that you will learn to explain the concepts of measuring and the many different types of modellings, as well as its application in precision and future farming technologies. Certainly an exciting area. And finally, this topic will enable you to build on your interpretation, communication and present ideas using appropriate technologies. In this lecture we're going to explore why we use modelling technologies in agriculture. I'm going to give you an introduction to modelling, which will include some definitions. We're going to look at two types of modelling, mechanistic and empirical modelling. We are also going to explore some of the advantages and some of the disadvantages of modelling. And we will finish with an example of a simple crop estimation model. There will be a couple of case studies presented. Before I introduce what a model is or can be, I want to start by a short discussion of why we use modelling technologies in agriculture. Well, it turns out that there are many potential applications. Some of them were listed on the front slide of this lecture. Let us start with one that is perhaps most important to you guys of where you are at the moment, and that is an educational one. There is a game or software that has been put together called Farm Sim. This simulates farm-like operations. You can pause the video now and have a look at the outcome of the simulation. In this preview you will see combine harvesters and tractors driven, and gives you an example of some of the outputs of the game. The aim of the game is to try and simulate what it's like to run and own a farm. This allows you to explore some of the conceptual elements. It's not completely real, but it does give you a feeling for agriculture. Please note, I'm not advocating at this point in the lecture that you stop the lecture and play the game. I have heard it is quite addictive. So education and perhaps fun are one reasons why we may use models and modelling technologies in agriculture, but there are in fact many. It helps us inform research, it helps us to predict research outcomes, it helps us to confirm our research understanding. That is, if we understand a physiological process correctly and we can relate it to a mathematical formula, if we can then predict the outcome correctly, this shows that we understand the concepts and the theories that underpin our hypotheses or our understanding. Education, as we've discussed, there are software such as SimFarm, but there also we can use it as simple yield predictions, as we will do later on in this topic, to show the principles of modelling. Prediction. There are many entities in agriculture where it is important to predict, for example, flowering date, degree days, climate, sowing date, your yield. These are used and wanted, and this information is wanted to be known in many agricultural enterprises. Modelling is often used to improve efficiencies and production. It may be used for disease control, and therefore it can enable the more efficient use of chemicals, for example. It may enable you to improve your energy efficiencies if you can measure and then monitor a system and model its potential outcome versus its actual outcome. This can tell you quantitatively how much savings you theoretically can make, and even in some cases identify where those savings can be made. And of course, perhaps the most important aspect is either directly or indirectly, all of these models should enable increases or improvement in profits. So let us start with the basics. A model is not the real world, but merely a human construction to help us better understand real-world systems. Modelling can be defined in general terms as all models have information input, an information processor, and an output of expected results. The type of model that you would employ will depend on a couple of elements. It can depend on your output and your inputs, or, and oftenly most important, the function of the model. What are you using it for? What's its purpose? The types of models we are going to touch on in these topics are conceptual models, physical models, the more commonly thought of one, mathematical and statistical models, and I will also touch on visualization models. Conceptual models are quantitative models that can help highlight important connections in real-world systems and processes. They are used as a first step in the development of more complex models. The following resource gives you an overview on modelling, it introduces it, and the advantages and disadvantages of conceptual modelling. It indicates or shows you an example of a blue sky conceptual model and a red sky conceptual model. Red sunsets and blue skies are illustrated. The intensity of the scattered light from the atmosphere increases with decreasing wavelength, a simple fact. In fact, the intensity of a scattered light is inversely proportional to the fourth power of the wavelength, is the example that is shown. The observer on the left sees a blue sky when looking up, and the observer on the red sky sees a reddish sun. More detail can be given, and this can be expanded into a mathematical model as shown in this link. Many introductory atmospheric science classes start with this example. Therefore, you can see how this is a useful teaching component. It enables the conceptual development, i.e., it enables you to understand how things work, particularly if you try to develop a conceptual model yourself. In the first stage of the development of the conceptual model, you will be developing quantitative models. Interactive development of a conceptual model can be used very effectively. This enables a potential student, for example, or farmer to engage in a learning environment and make the concepts and themes quite simple. Participating in the development and then the subsequent validation of conceptual models, we'll talk about validation later, helps you understand different physical processes. So let us start by demonstrating a simple conceptual model. Here we have one of plant growth. I have shown this model by a mix of an image of a plant and words that indicate the input that enables growth. None of this will be a surprise to you. A plant needs water, carbon dioxide, sunlight, and a suite of nutrients in order to grow. In your conceptual model, you have hypothesized your inputs for plant growth. The next stage you might make is to take your conceptual model into a physical model. You might try by understanding the relationships. So what happens if you get more sun or less sun to plant growth? Does it increase or decrease? You can examine and explore all of these relationships for all of these inputs. There have been many years of science looking at all of these inputs, in fact, and how they impact on plant growth. One very interesting and extensive amount of work has been done on plant nutrients. As a rule of thumb, a simple one at that, the more nutrients you apply at the correct time, the better your plant growth. You might set up a suite of experiments in order to try and understand this relationship better. The most recent experiments I could find on a quick search was by Peng Han et al. In 2014. These scientists were looking at the relationship of nitrogen and water availability to tomato plants. They have reported nitrogen input against time after sowing. This is one example of such data that you might start to put together in order to understand your model of plant growth. Physical models are another type of model. A physical model is a system that can be easily observed and manipulated and which have characteristics similar to key features of more complex systems in the real world. Most commonly, a physical model is referred to as a simple model, but it can be distinguished from that of a conceptual model. The geometry of the model and the object it represents are often similar in the sense that one of them is rescaling of the other. In such cases, scaling is a very important characteristic of physical models. In some cases, however, scaling is not that important, and simplicity or approximate scaling is what is required. The following is an example of a physical model. This is a physical model of a spray drift from broom sprayers in agriculture. In order to facilitate crop protection, understanding how efficient spray drift is important. Please refer to the following URL link where you will find a PowerPoint. This PowerPoint gives you information on how this model is constructed. This case study shows you how the elements of the model have been constructed. The model makes a number of claims. It claims to be able to stimulate spray drift from conventional boom sprayers. It claims it is useful for a tool for drift hazard assessment. It claims it is a useful tool for nozzle classification and is useful to understand drift as a hazard. The next group of models I'd like to introduce are those of mathematical and statistical models. These involve solving relevant equations of a system or characterizing a system based upon its statistical parameters such as a mean, mode, variance, or regression coefficients. Mathematical models include analytical models and numerical models. Statistical models are useful in helping identify patterns and underlying relationships between data sets. Please follow the following URL link for examples of mathematical models. You may have noticed that a mathematical model can be used as part of a physical model and or a conceptual model. A visualization model is a model that can be a direct link between data and some graphical or image output, or it can be linked in a series with some other type of model, so to convert its output into a visually useful format. The example shown on the screen is a model based on the mixing of two fluids. Scientific visualization is another term for visualization models, and it is an interdisciplinary branch of science. It can bring together architecture, meteorology, medical, biological, and the emphasis is on realistic renderings of volumes, surfaces, illumination sources, and so forth. There is often a dynamic or time component as part of the model. It is considered a branch of computer science. I believe that there is great potential for visualization modeling in agriculture, particularly in production outputs. If you can see how something is physically changing with your production inputs, then you might be able to conceptualize better how those relationships are working. So in the next section, we're going to look at some of the important aspects of models. I want to start with units and conversion factors. This can cause problems, so to avoid confusions and errors, a standard system, the International System of Units, SI, was developed by the Royal Society in 1975, and it is considered good practice to use the SI system of units unless there is a very good reason for not. Some examples of SI units: mass is stated in kilogram, length in metre, and time in seconds. It is best to use the correct units, as there could be some confusion. One of the more commonly seen areas of confusion is that when you are changing from a concentration to an amount, or vice versa. Units can take a number of levels as well, and it is important to put the levels into your model correctly. What I mean by this is dynamic models of crop growth may be a change in growth over time, such as a day. So your unit becomes kilogram of growth per day. It is important that you enter your units correctly, that you follow them through the system correctly, and that if you convert them, that you understand the conversion that has occurred and that no error has been made. Another type of model category is that of either discrete or continuous modelling. Note, this is different from static or dynamic. A discrete model treats objects as discrete, such as the particles in a molecule model or the states in a statistical model, while continuous models represents the objectives in a continuous manner, such as that of temperature measurements. You may have come across the differences between discrete and continuous in statistics, and these differences apply here too. Both of these models can be applied in agriculture, but it does depend on the specific application or function that you are trying to achieve with your model. When you are crop and plant modelling, or indeed if you intend to model animals, there are two different types of models that you may engage. You may engage either a static or a dynamic model. If you want to model crops, a dynamic model is best suited. A dynamic model accounts for the time-dependent changes in the state of the system, while a static, or sometimes referred to as a steady-state model, calculates the system in an equilibrium, and thus the time is an invariant. As crops grow and animal grows, you need to incorporate time, therefore you need to use dynamic models. When you are considering using models from a scientific aspect, that is, to increase knowledge in the area of science, the following should be considered. You should determine whether the model will be applied or strategic. The use of the model, for example, an increase in efficiency or improvement to the environment. It is important that the observational data is coupled with a theory or a hypothesis or conceptual scheme that corresponds to your data. And look at how your model is going to work. A continual interaction between hypothesis and observational data, producing an outcome of increasing in understanding and/or efficiency, is the gold star, or what we hope the model will achieve. I want to touch on the role of mathematics in models. A model often examines both the quantitative and the qualitative aspects of a problem. While theory and experimentation are usually described by mathematics, it is important to emphasize ideas and hypotheses of a theory and not completely rely on only the mathematics. This means that you can get a mathematical equation which doesn't necessarily underpin any phenological or physiological aspect of your system. And this is what Thornley and Johnson in their 2010 plant and crop modelling were relating to. Models in agriculture and horticulture are used for three main purposes. There is reaffirming or building on traditional knowledge. There is scientific knowledge. And it is also used as conjecture or guesswork where a novel solution is required. And in the FAO resource, an agricultural system is an assembly of components which are united by some form of interaction and interdependence, and which operate within a prescribed boundary to achieve a specific agricultural objective on behalf of the benefits of the system. This statement is quite long and may not make sense at first, but what it is defining hierarchical systems. Let's break it down into its simple components. An agricultural system is a number of components. It's a field, it's a farm, it's soil, it's a crop, it's a cow, those sorts of things. And these components can interact together and they can act interdependent of each other. But there is a single boundary that defines them. That is, they are all a part of the farm. And that all of these components benefit the system. Hierarchy systems are another component that you need to factor in when understanding modelling. The definition of hierarchy is anonymous to the general definition of artificial, man-made system of which all managed agricultural systems, including specifically the farm level system, form one subdivision. In plant biology, there are many organisational levels that you need to consider when constructing models. On the slide, I have given you an example of a plant biology hierarchical system. There are many organisational levels. You can think from the smallest to the largest or the largest to the smallest. It is size that has defined my particular hierarchy and is what I am describing here. For example, a crop is made up of plants. Plants are made up of organs. These organs are constructed from tissues. These tissues are constructed from cells. Within these cells are organelles. Organelles are made up of a combination of macromolecules, and macromolecules are made up of a combination of molecules and atoms. I have not given an example below at the size of an atom here. I have given you a link on Moodle to the FAO site that defines hierarchical systems on farms. This is a very useful resource. I'd like you to refer to this resource to complete the table. I'd like you to find out the proper description and give an example of each of the order level hierarchicals from 1 through to 12. I have done number 1 and number 12 as an example. So order level 1 of a hierarchical system, the farm, is a unidimensional process system. For example, it could be a single fertilizer element such as nitrogen. You can fill in descriptions hierarchical levels 2 through to hierarchical level 11. The highest order level is 12 in this system, and this is the farm household system. An example of this is a whole farm and its associated household respectively. The contents of this slide are derived from the reference Thornley and Johnson 2010, and they reinforce all of the components of why hierarchical levels are essential to understand from a modelling perspective. Each hierarchical level has its own language that is unique to that level. Each level is an integration of items from a lower level. Successful operation of a given level requires lower levels to function correctly and vice versa. The higher levels provide the constraints, boundary values and driving force, that is, inputs and outputs, to the lower level. On descending to a lower level, generally both spatial and temporary scales become smaller. Smaller physical size and in many cases a faster process. Now let us move on to empirical models. An empirical model is a direct description of observational data. An example of an empirical model might be of that of tidal data. Any mathematical relationships used in these models are usually unconstrained by physical laws, or the laws of thermodynamics. The empirical model describes a level of behavior, observational data, by terms of the attitude alone, with regard to the biological theory. In summary, an empirical data represents the data and no information is required. Here is an example of a simple empirical model. It demonstrates the relationship between crop yield and nitrogen fertilizer. The observational data is recorded as crop yield. 2, the level of nitrogen fertilizer. These are the treatments applied in this example. Why the plant behavior was observed is the question. The model contains no information about the original data. It contains no information about the mechanisms in the response and why these mechanisms occurred. The line that you are seeing is described as a 3-parameter rectangular hyperbola. The formula of the relationship between crop yield Y and nitrogen fertilizer level N is also shown on the graph. I want to draw your attention to some expectations of models and perhaps some guidelines that should be used around your expectations. It is always important that you take some time when using a model to understand the model assumptions. Does it only work between a certain temperature range? Will the model not work if it's too humid? These sorts of things. Ensure that you defined the output correctly. Is your yield, for example, in a productivity model, on a hectare base or a weight base? This is quite an important differentiation. Ensure that model type matches its required function. You don't want to use a visualization model, for example, if you need a quantitative output. Understand the model's limits. Often models are set within certain limits. These limits are usually dependent upon the input limits, for example. You may set up a model to understand nutrient uptake in plants. If your nutrient applied is far greater than the model's limits, then you need to disregard the model output, as you do not know if the relationship holds outside the model limits. And do not try to draw conclusions that the model was not designed to determine. This is an easy trap to fall in. So, how do you develop a model? Well, the methodology that you use is very specific to the type of model being developed, but there are some generic stages that are followed. The 3 main stages are model selection, what model do you use, model fitting, and model validation. So, you need to decide what model you are going to use, what enables you to fulfill the function of the model. You then need to construct this model. Data then needs to be fit into the model or algorithms written for the model. The model then needs to be tested and validated. This stage is essential to get right. Usually testing is with blind data, and the validation is that if the data comes up with your expected results, then you can say that your model is being validated. You need to validate your model when you are working in agriculture under a number of enterprises and conditions in order to assure that it is robust. The development of models takes years and years. Years of data input, years of experimentation, years of testing, and years of validation. To learn more about the steps in developing a model, please refer to the following website. This describes the basic steps and includes a very informative flowchart that will enable you to see the simple steps that are required. After this lecture, you will be required to complete the tutorial exercise that is associated with this topic. It is an example of a simple crop estimation model which was developed by Department of Environmental and Primary Industries, which is now called DEPI. On the Moodle link, there will be a link to DEPI Estimation Crop Yields, a brief guide. You will need to read this guide and complete the tutorial exercise. Once the exercise is completed, insert the exercise into your lecture notes here. For case study number 1 exercise, you will need to read the Robinson and Kierkegaard 19th Australia Research Assembly on Brassicas Conference Proceedings. This article is on crop modelling for the Australian canola industry, a review. This can be found on Moodle. Also on Moodle will be a file containing the case study exercises. There are a number of questions associated with this case study that you are required to answer in order to complete your lecture notes. For case study number 2, you'll have to refer to the following URL link. This site is called My Agricultural Information Bank. Please read and make notes on the modelling described on this resource. There are 6 types. Put these types of models into your lecture notes here to complete your lecture notes on this topic. So let us summarise what we have learnt in this lecture. You should be able to understand and give examples of the different roles of models and the different roles of models in agriculture. You should understand what models will give you what functions, and therefore which types of models would you select. We have covered in this lecture some important aspects of modelling. For example, is your model a discrete or a continuous model? What is the role of mathematics in your model? Have you thought about unit and conversion factors? And how have you allowed for hierarchical components in your model? You should be able to now understand what you should expect to get from any one kind of model. You should understand the assumptions from any model that you use. You will have an idea about how to build a basic model. And to complete the lecture, you will have completed the case studies and the tutorial examples. This brings us to the end of Lecture 11 on models.